Okay. Hi, I'm Kritik. This is Arika. I realized today that these colloquiums have an intro slide, but you don't have to look at those very old photos of us speaking with here IRL. Yeah, so this is today, this talk is going to be partly a presentation I did a few months ago at a conference called Constructionism. And then the second half would be hands-on, interactive. I don't know if people online read the blurb, but I put a link to print out a document which can let you be online, interactive, and do the hands-on activity even if you're online. So if that works out, it'll be awesome. But I can share the screen and show what's happening at that point as well. Okay. So what? Oh, it's very old, and somehow both of it are graduation photographs. Oh yeah, I guess a little bit about us. I'm fourth year PhD student, or I guess candidate now here in CTD, Creative Technology and Design.
I'm a second year PhD student here at Atlas.
We're both in the Acme lab. I'm also advised by Mike Rivera.
I'm also advised by Mark Gross and John Keller at Fisk Planetarium.
Cool. So I like to start these presentations with this picture. Does anybody know what this is? Anyone? Of course, I just told me you've seen this 4 times. This is Banu Musa's music automaton from 9th century. It's possibly the very first programmable machine that we know of. And it's similar to those music boxes that we find in gift shops today. And to highlight what's most fascinating for me and for the book where I found this from, I'll quote the author. For 800 years, humans had possessed the protein source of programmability, and over that time, they only used it or exclusively used that resource to generate pleasing patterns of sound waves in the air. What this really shows how it highlights the connection between computer technology from the very beginning and human creativity. Since the beginning of this field, we've used it to be creative as an extension of our creativity. And that's kind of what we're going to talk about today. Creative learning, as people might be familiar here, are experiences that are open-ended, creative ways to learn with technology. This form of engagement is driven by learners' interest and motivation, and often involves playful, iterative exploration. It's not only for learning about computers or learning programming, but for any STEM fields, and it enables students to make meaningful computational artifacts. So, for example, you could be learning about electric circuits by building an elevator to investigate how the elevator works. And a high school student in a lab actually built a whole elevator for that purpose. Yeah, so this creative learning idea is deeply rooted in education, pedagogy, research, especially Seymour Pappert's theory of constructionism, according to which we learn by constructing our mental models and building physical artifacts like sandcastles, which is a famous metaphor that he uses a lot. We've seen these practices of tinkering and creative learning, especially utilized in tools where we learn with computers. Wilkinson defined computational tinkering as a playful approach to constructing with code. And computational creative learning isn't just limited to coding on laptops, which is what we see with things like Scratch or MakeCode or anything, all these apps that exist these days. In the past decades, many researchers have also explored how tangible interfaces can enable children to learn with computers out in the real world. This ties back to this old quote from Mitchell Resnick, who is actually the creator of Scratch. Before working on Scratch, he mentioned, instead of controlling and manipulating worlds in the computer, what if children could control and manipulate computers in the world? And that's the central idea of interacting, learning with tangible interfaces. So researchers have explored many benefits of these in learning environments. They're natural, they're more intuitive, they can be more engaging and collaborative, and they also foster experimentation and divergent thinking, which is obviously very useful for creative learning. In my own PhD over the last 3 years, I've been trying to design ways to empower and create, enable students to create and learn with technology with real physical materials. For example, one of the projects that people definitely would be familiar with is Cartoonimator, which is a paper-based tangible kit for keyframe animation. Keyframe is a common technique in animation software that enables us to animate a whole scene or a whole movie by just a handful of frames that we define as keyframes. And in this particular tool, Cartoonimator enables you to turn your drawings on paper into animations in like a few minutes. And we'll actually use a version of Cartoonimator later in the hands-on activity. This software that I developed fills in all the gaps between all the photos that you take. So instead of doing stop motion with 50 different or 100 different hand-drawn things, you could draw 5 things and make a full movie if you want. The kit that I developed consists of paper templates with background sheets and object cards for scene background and the characters respectively. And then you use the app to capture the keyframes, for example, this, and then you can play the animation after you've done a few captures. I just realized I'm moving back and forth, but that doesn't really make sense for people online. I'm just pointing at things on the screen. And over the years, I've had the opportunity to try this out with kids and adults in different settings like workshops and single individual studies as well. And we've seen a lot of animated creative stories, but also very unique ways to utilize the template that I hadn't previously expected. And that's something about the paper-based tangible interaction, which we highlight again. So in today's talk, I share the work we did to develop a broader understanding of these creative learning interfaces, specifically the tangible interface for creative learning, like Cartoonimator, which enable learning in a computational media through an open-ended tinkering ideology. So we particularly focused on the design of these interfaces. We conducted this survey of projects to help us make sense of the wealth of work that exists and also inform future designs of these interfaces, as well as my own work, our own work in this lab. So in the second half of the talk, that's why we'll go back to one of these projects that emerged after we did this analysis, taking in all these learnings and how that can actually be used in real contexts. So for the first part, where I'll talk about how we sampled 33 different projects to basically investigate these two questions. What do learners tinker with and how do they tinker? So before going deeper, this is a brief outline and this will be very quick. I set myself up for 20 minutes, but I've already talked for 10 minutes and 5 slides. So I should hurry up a little bit. I'll first talk about the method, how we investigated this, and I'll talk about the two results that we got from this and what that means as a design implication. And finally, we'll dive into the activity. All right. So, as I said, this was a literature survey of a small sample set of papers, 33, and we used purposive sampling, which is an interpretive technique. So we didn't just do a keyword search and found 50 things to analyze. We knew about these projects. We found other projects that were unique and characterized different things that we wanted to investigate. Basically, the projects involved were things that had tangible interaction, things that were computational, and things that enabled an open-ended outcome, which sometimes can be rare, as we find out. So this included projects like Roberto, which is this sticker book on which you can put stickers, and it comes with an accompanying app. And the stickers basically let you animate the character either according to the story as it's going in the storybook or very different from it, however you would like. Or Sensor Bricks, which is this physically tangible toolkit for interacting with data and building these data tracking tools. And Strawbees is this interface with wooden blocks and an iPad that lets you learn coding by making a game or interacting with the game. It allows for both. And the idea of the game is for the character to eat as many strawberries as possible. Strawberries is a cool word for strawberries. Um, which people will be familiar with, is Roblox. And let's see if I can do this. That lets you very quickly create these robots using blocks. And There you go. Hypercubes lets learners develop games in augmented reality with similar blocks, but these are not electronic, and you use an iPad to overlay and see. And lastly, TADCAD is this tangible token system that lets you create parametric 3D models with a tangible interface to learn about what parametric design means. So obviously, we analyzed 33 different projects, as I mentioned, but that's a lot to talk about. So I'll stick to these 7 and talk about all our results with the context of these 7 projects. Did I miss any? You're right. Oh, sorry. So essentially, we looked at these projects through 3 dimensions. First was context. Oh, I realized why I have been having to look back so much, because it's so small here. I can't see it. First was context, which answers the question, what are learners tinkering with? Which involved looking at the learning goals, the project outputs, and what are they creating with these interfaces. Second was tangibility, which ties to the question of how do learners tinker. So here we looked at how tangible interaction was really utilized in each of these projects. And lastly, we looked at expressivity, which as I'll explain later, but the idea was how open-ended it was. What was the opportunity that the learners had to define their own goals or rules for creation. So let's start with the first question. What do learners tinker with? Overall, in the survey, there were so many different learning goals. Only some of which the most prominent ones are outlined over here. The most common were programming concepts and computational thinking, as you may expect, which were seen in projects like Strawberries or Roberto, where you're using these components to learn about logical flow or programming logic. But then there was also stuff like TADCAD, which let you learn about 3D modeling and parametric design. Then there was a different idea of project output. So there were things like Cartoonimator, where the output, what you're creating is an animation, or Hypercubes, where you're creating these AR interactive artifacts or games, even in some cases. So projects like TADCAD and Cartoonimator had a matched output to the creation. So what that means is you learned about 3D modeling by creating 3D models, or you learned about animation or keyframe animation by creating animations. But in some projects, like in Roberto, you were creating one thing in service to learning something else. For example, you're learning about programming or logic by making animations in case of Roberto, or you're learning about complexity and complex systems by making robots in Roblox. So, okay, moving on to the next question. I'm still keeping on time. Okay. First part, as I mentioned, was looking at tangible interaction. How is tangibility utilized in each of these interfaces? And with that, looking at all of these projects, we developed a taxonomy of what tangible interaction meant in this case, which basically means different ways tangible interaction or TUIs were used in the interface. So for example, in a lot of these projects, the tangible tokens or blocks were used to represent code. Like we saw in Roberto, or what was the other one? Strawberries, yes. In some, they were also used to represent data, which meant like properties of a character, like the size or the animation that you want to associate with it. They also meant sometimes physical construction, like in Roblox, where the blocks that you're connecting together are actually forming the physical structure of your output or robot. And this also involved environmental sensing, where there were sensors that you could utilize to interact with the environment, the space, and yourself. In some of these, like TADCAD, there was movement that was being tracked. So that's another way tangible interaction was utilized. And in a few, like Cartoonimator, or you could actually draw, and that was the way you're tangibly interacting with the thing. Lastly, some of them had assembly of circuits as the interaction that you're engaging with. This is like the general breadth of the different ways TUI was utilized. And then that ties into coupled versus uncoupled. So what that means is there were projects where the output was different from the input. For example, strawberries, where you're interacting on the table surface and you see the output as the game on the screen. Or Roberto, where you're sticking things on the paper and you're looking at the animation on the iPad. But then there were also projects like Hypercubes or Roblox, where the output and is coupled to the input, where in case of Hypercubes, you're looking at the output on top, overlaid on the blocks through AR or augmented reality. Or in case of Roblox, what you construct is the robot itself. And this obviously has implications for like how we're learning, because then we, in terms of psychologically, you're not disconnecting. And I'm not a learning scientist, so there's a lot of research that people do on this. And lastly, there was a few projects where it was both. I should have deleted this slide. It's fine. So okay, this is the good part, right? What were the implications? What was the point of all this? Firstly, what doing this helped us discover is a spectrum of tinkerability. Like all of these projects, we selected to be open-ended, to be creative, but even in those, there were a degree or spectrum of how expressive or tinkerable these were. And this was generally defined, or we defined based on some prior work, according to these three categories. So there were some projects where the learners were defining the rules of interaction, but what they were creating or the goal towards they were working was predefined in the interface. Then there were projects where the rules were predefined very strictly by the interface, but the learners were able to define their own goals and take it however they wanted to. And lastly, the most expressive were things that were learner-defined rules and goals. And it looks like three columns, but this really was a spectrum where things, as I just described, were somewhere in the middle sometimes. For example, in case of the animation domain, there was things like Roberto, where you could define like that you're following the story, but you could change it up to animate the character however you wanted to. But in case of cartoon animator, even the way you interact as well as what you're creating, the kind of animation you're creating is defined by you. So that's very learner defined and learner defined rules and codes. But in case of games, there was stuff like strawberries where the goal was very much predefined by the game, which was to capture the strawberries or eat the strawberries. But you're interacting with the interface in very free-form ways to work towards that goal. But in case of hypercubes, you're basically making your own game with these blocks and by putting these blocks together. So this kind of helps us look at what does expressivity mean in creative learning interfaces and how can we try to push the projects towards the right. Now, the second insight that we arrived at was the need to expand beyond code. So obviously people, especially in a building like this in Atlas, we would be familiar with all these different ways we can be creative with code, starting from logo, which was invented in 1960s, or Scratch, which is kind of a much younger relative of logo, but even working in text. But all of these are like ways to code in different ways, in interactive ways to develop stuff. And we saw a parallel of that in tangible interfaces in our survey as well, whether it's writing code through wooden blocks and strawberries or through stickers, or actually constructing code with tangible blocks in Roblox. But on the other hand, we also saw a lot of projects that were letting you create computational artifacts without code. Like in case of cartoon animator, you're placing these cards on the screen and taking photographs to animate your story. Or in case of TagCAD, you're manipulating these tags to construct the 3D model that you want. Or in case of sensor blocks, you're working with data in a much more embodied manner. In my own projects as well, like in Cartoon Animator and some other stuff that one of which we'll try out later today, I sought to enable interaction that doesn't just revolve around code, that doesn't just mean writing block-based line after line logic. So the third insight, which I'm very passionate about, is increasing access with materials. And a lot of my work, especially around paper, comes from motivation of working in contexts where there aren't computers for every single student, or there aren't computing devices that are readily available, or even if they are, they're not that great. So this is something I was very interested in looking at, which is how are researchers and people making these interfaces very easy to deploy in all sorts of settings. So firstly, a lot of these projects were passive, which meant there was no integrated electronics in there, which obviously makes it much easier to replicate, makes it much easier to put in different settings at a low cost. So this usually involved using paper, or in some cases wooden blocks, or like 3D printed or acrylic tokens in case of TATCAP. Another way these projects made things accessible was using mobile devices, which are getting cheaper and more accessible every year, especially not in the US as much because iPhone monarchy, but around the world, Android phones are cheaper and much more powerful and are being used in educational contexts a lot. So that's something a lot of these projects also used to make them more accessible than like full-fledged PCs around the classroom.
Could you argue that the electronics are more accessible than the blocks?
Yes, I can, and I'll talk about that in a second. Because here, in case of actually, oh wait, that's a slide I should not have deleted for your question. But a lot of these blocks involve custom electronics, which makes them inevitably cost a lot more. So like Roblox, a set of Roblox, the basic one is $250. Or each of these things where researchers are making a custom chip to put in there, unless you reach the level that Lego Mindstorms has, it won't reduce in price. And even at Lego Mindstorms, they're not as cheap as Lego, obviously. So there's using passive blocks can be. I guess one aspect there is that in case of mobile devices, they're not single purpose, but most projects like Roblox are single purpose. You just use it for that particular kit and that's it. And one way people tackle that is either through DIY interfaces. So two of the projects that we saw involved documentation good enough for educators and students to replicate the toolkit themselves in their own space with like materials such as paper. And this is actually from our lab. Ruhan developed this paper block robot or like copper tape, things that are mostly available for not a lot. But another way was using commercial platforms. So like people might be familiar with things like Arduino and microbits and Picos, which are general purpose microcontrollers. But if we were to build out sophisticated tangible interfaces using these existing platforms, then they're not single purpose, and then they can be used in a lot of different contexts. So you're not just getting this custom electronic piece of hardware for one thing. And that is, I would think, more accessible in many ways.
Well, that begs the question about the virtual world and accessibility versus the physical world and accessibility. And
Oh, yeah.
you know, it's like tangible interfaces. It's great, but how do you overcome the accessibility issue around it? You know what I mean?
That's been the biggest struggle I've had. Like I'm an electrical and computer engineer major from before, but since I've come here, I've only done CV because electronics are just by default not going to be as accessible as paper and cardboard.
Computer vision.
Yes, computer vision. Sorry. Okay, so that was the third thing. Whoa, this is already 25 minutes. So we're gonna skip. This is the last part, the hands-on part. So while Erika is bringing the materials, I'll just basically give an overview of what we're going to be doing now. So based on all of these things that we learned from the survey and from all the other projects like Autonomator, we over the last year have been working with astronomy educators in at CU Denver, like for who teach undergrad beginner introductory astronomy courses, to develop this toolkit that enables creative learning in astronomy. So here, the goal was for students to learn about Kepler's laws. Who knows what's Kepler's law is? Yeah, I see very few hands. So this will be fun because this is how we'll actually learn if you can learn from from this interface about Kepler's laws. So okay, overall, this is similar to Cartoonimator. It's kind of a spin on Cartoonimator where there's a paper background, which is where, okay, yeah, we have enough time. So what we're going to be doing is we'll spend some time, there's markers and stuff. We'll spend some time to create our own space, something like this, or and however you may want, and then create assets for a sun, a planet, and a focus. And focus we'll learn about as we go because it's the fun one. I won't explain right now. So once you have drawn this, which will, let's take the next 5 to 10 minutes. Yeah, actually, I'll leave it at this page as we distribute stuff and give people time to sketch things out however they may want. And people in the back want to move towards the table. I might actually move that table up, so that's more table space.
So the sun. The sun, the focus. I have a planet.
Jamaica.
Planet, the face, apparently.
There's no chance I'm doing one of my own.
Well, you already know the planet, all the sun, planet rotating, all the sun is rotating.
Planets revolve around the sun. So
Are we getting?
you may draw a planet or you can
The
draw
cards
anything
are for the
else.
sun, right? We're gonna be making cards.
This is a word. So if people wanna.
First, make.
Is that it?
That's
Yeah.
like construction, yeah.
Is this, would you like to help me draw some space? Here, you take that side.
Oh, got rest space, whoa.
I don't
They took.
want to
out-
influence any
It
decisions,
is what it is. It's.
but here is a cat asteroid that somebody drew in one of our classes. Because they wanted a cat to go around the sun.
Is that the focus? Wait.
That's the
That was one of the asteroid, one of the planet, yeah. So you see that cat was moving.
yeah.
So we're just.
Oh, yeah.
We're not adding.
Okay.
And now we'll go around and give out the cards for sun, asteroid.
Alright, which one's sun?
The yellow ones are sun.
This is the sun, okay. And that's the, wait, how many suns?
We have two sons.
We have two suns.
Does it have
Oh,
any significance?
Or two people, so I gave you two sons for that.
Can I just?
We're a team.
I'll watch.
We got crazy stuff. Universe.
Right, my sister said, like, now, you know, when you're not working and you're studying, you don't really have weekends anymore.
In a good way. That's probably
I
not.
have a, came down from Summit County, she's pregnant, it was really good to meet her and catch up, she's gonna be busy soon.
Also, I don't like to ask this, but if somebody really doesn't like to draw, we also have printed ones.
Use other people's sun.
Yeah. Lost out, basically.
Thank you.
Yeah, I can get you to like draw cards.
So people online, I'm gonna put up a webcam and then walk around with it as much as I can.
You can judge our
I'm
design.
watching you through the owl, so it's just fun.
Oh,
you
okay,
can
but you
see
can't
it?
see the drawing, so I'm gonna make that happen.
It's okay to clear that.
Oh, beautiful.
I feel like a 5-year-old now.
Am I limiting my tinkerability by wondering what we're supposed to be doing?
You can order whatever you would like.
Right on whatever.
That's part of it. The whole idea is that it's learner driven, so yes.
Yeah.
It's good to be wondering
Okay.
why we're doing this.
Okay.
Yeah.
Yeah.
Did you guys
There's a
toss
version
me
of this
that
where I
purple first?
ran through the whole thing
Right in
before,
front of your.
but I think this is more.
Thank you.
Can I trade you?
Okay, now.
Can you hear me?
webcam show all the creativity.
Great work, everybody.
Which, one thing I always forget to mention is try to make the things darker, like the sun and the asteroid.
Right, so you can
Because
be.
this is very bright room and it might disappear.
You might disappear.
But
Okay.
it's- You'll see what I mean.
Yeah.
Like, yeah, just make it darker strokes.
So you.
No, why did that go? So
What happened? Try again. Like, turn this back on, I think.
Whoa, lovely.
Yeah,
Oh, there we go.
I think the projector is on strike.
Maybe we can turn this one into.
No, what's the focus? Or we don't know yet.
You don't know yet, you can draw whatever you would like.
Oh, anything.
So every orbit has two foci. One is the sun and the other is this hidden focus that's not actually an object, but that's how mechanics works in the space.
Oh, you draw
So
the
it's not
equilibrium.
it's not a focus to the planet, it's a focus to anything.
Is it invisible?
Now,
thing.
every planet will have two foci.
Okay.
One is the sun and the other is this weird invisible thing that, let's see, when we interact, if we can discover the meaning of.
Okay.
Ah,
How's drawing going?
doing fine.
Really good.
Karthik, can you hear me?
Yes,
Yes,
I was gonna ask you if this, by your definition, is coupled or decoupled.
this is decoupled.
Okay,
Because what we're gonna be doing is after we create all these paper templates, we'll use our phones to make the animation and the simulation of the orbit will show up on the phone, so it's decoupled.
Are noises allowed?
Oh. They are allowed. You can make the noises as the simulation is going. You are the noise
I
generator.
need to do that.
Yes.
we're just not recording the
Let's see if we
the
can.
noise.
Oh, wow, that's it.
Yes. What happened?
Oh, you have your phone, yes.
I guess.
You're joined? Oh, on the phone? Oh,
I'm using Rishi's phone to go walk around.
that's
Oh,
cool.
cool.
Yes.
I'm sitting in your seat, so
No,
I
you're
feel like
good.
my mind is enhanced. Know what I'm
You
saying?
know exactly
Yeah.
how this works and everything. And you open the zine and everything.
Open the zine. Ah.
Okay, so while I think people are mostly wrapping up with the drawing, so I'm gonna shift attention back to
All
the
right.
theory so that we can talk about what's next. But you don't have to stop drawing. I don't want to stop anybody from doing what they want. So okay, what we're gonna do is we'll open up a web app that I'll show QR code in just a second. In that web app is where we basically are gonna build a simulation for the orbit that we just created. So first step is capturing the background. We'll hit the capture button on the background thing and take a picture when we see the white check mark of the background space that we just drew. Make sure that there's no objects on top of the background when you're doing that. Once that is done, we go ahead and place the sun, the focus, and the asteroid on top of the background, and then take another capture for the objects. So this is what's telling the simulation where you want all of these things to be in your space. And then, quite simply, hit play, and then you'll see a simulation made out of your hand-drawn space. Here's the QR code.
All right, let's go.
Oh, actually, I didn't test. This might be the old code. Let's see.
Yeah, so. You,
I love how he's just going with
That's fine. That's the feedback. I gotta go down.
This is not the right code.
give us the right.
1 second.
We do feedback before we do animation?
Yeah.
I'm gonna.
All right, quickly give us the QR code.
All right.
Got it.
That's not the right code.
Are you stealing all of my information right now?
You
I mean-
don't have to fill the form.
There's the.
Actually, don't fill this out.
Yeah, my QR code right
Oh,
here.
yeah, that's.
That one work.
No, don't. You
Don't do that. Don't
Don't
do
fill
that.
out the form.
Don't fill out the form before you do that.
Actually, you don't have to fill out the form. That's on me.
Create your own planet. Okay, allow the camera.
Okay.
That way.
Okay,
First without the, just
First,
background.
Without the object,
Text,
just the
the
background.
Okay,
Allow.
See the
Wait, hang on
screen?
the other side. Back camera.
Yeah.
Yeah.
Yeah, it's,
Alright, capture, I got it. Nice. Alright. And then.
cheers. Oh,
Object.
you can find it.
It's like fun.
Oh, you found it.
I don't know how to access it.
Did you
Use
get
the
it?
That
one
would be
on
for
the
me.
specific for not that one.
Oh, I got it.
Okay.
Did you?
It's just one. That.
So you, when you're
Like that.
capturing, you want to make sure that the entire page is visible.
Oh, the full.
So you maybe,
No, try that, okay, see that one.
yeah,
I think that's too many.
Get out of my life. Do I want the
Yeah,
black
yeah.
corners of the page?
yes,
You want the black corner, that's the
Right
market.
there, it's
to
Those,
recognize.
yeah, those are my fiducials.
Yeah,
yes. There you
I
go.
think you got catchy
Scroll
shadow.
down, you'll see.
So-
Capture.
So maybe. try
Now
it this
Now you
way.
can place the
Place
things.
my
objects.
Is it better?
No.
Huh,
Can I take a look?
Yeah. It's just not giving you that.
So you're just waiting.
I need to find the full corner, yeah.
What is it?
I did.
You were
See if I can
You're back.
Oh, got it.
try it.
But I just did.
Here's
I
the.
just captured it.
What? This is Chrome, right?
So, yeah, it's like the profile, but not less. What do you think about?
Oh, there you go. I think.
Alright.
Go through the permissions.
Alright. Okay, well, now we're in business.
Okay, alright, I'm gonna do.
Please, go ahead.
Done.
There's a
I can't
simulation.
even remember what I have.
So what do we think second focus is?
The other, I mean, the other point on an ellipse.
Yes, yeah,
Yeah.
But do you see also the speed of the asteroid changing?
Okay. Yeah. I had it.
Okay,
What do you think is happening there?
Are you supposed to do these individually or all together?
I
think together on your back.
Right?
Yeah.
Together
Further
on the
away,
back.
But it like.
That's
is
what I
anchored
understand.
to the-
Exactly.
I'm not
Yeah,
reading directions. Winging it.
You know.
bye. Very funny.
Is this what?
Not bad, yeah.
Oh, they went all, okay. I mean, yeah, that looks good. Do place the things closer. Because I think because the sun and the focus are so far away, basically it's making an ellipse like this.
Oh, I see. Oh,
Yes, it's Eclipse, right, so you have like 2 points.
Oh no, I lost my sun. Where did my sun go?
The sun stays still on the
But it
background. so
doesn't, it
it
doesn't
doesn't
even,
care.
it doesn't show up on mine.
It's only the background on my.
Well, my son. Yeah.
Let me see yours.
My son is.
I bet you did it right. You're the kid in, oh my God.
Get it all.
You're the kid in class that was successfully orbiting over here.
Yeah, you got.
Oh my God. You get the star today. That's pretty cool.
That's pretty cool. Huh? We're so excited.
I know.
And get down with your movie too.
Oh, yeah, yeah, I've gone outside the borders, I colored outside the lines as usual.
Oh, yeah, okay.
No, you're capturing them all individually.
Whoa, that's
Right,
that's
exactly.
awesome.
I think it's just.
You can also download it.
Yeah, that's so cute.
Did it work on yours, Ali?
Elliptical?
Yeah.
Oh, yeah, that's very good.
It's very good.
It's gonna collide into the sun. I like how you have a humanoid asteroid.
Happens.
Download. I can download my video.
Okay, yeah, I mean, this is just general playtime, but I can also answer any questions if people have about the dog or about this, or why are we doing whatever this is.
Why are you doing this?
I had a question about, so you were looking at like 33 different, how many of them like had like. Talked about like how they introduced it or if like they debriefed after, like for the learning part of it, and like,
Oh, yeah.
yeah, I'm curious like how many of them talked about that, like if they were like,
So
or if they just talked about the tools.
weirdly enough, a lot of these projects that we looked at, and a lot of these projects that I tend to find tend to be works in progress or short papers, which is like, this is a cool thing,
Oh,
cool
no,
interactive thing that we made.
You have.
And then you don't always find the learning science paper about what it meant for the learning. Some of them definitely had that. as well. This was early on in the survey where I was also looking at how they investigated the learning outcomes and stuff. And some of them definitely had questions like whether engagement is happening or whether they're being creative. One thing I would say is that with constructionist learning and with creative learning in general, focus is a lot more on how they're learning and what's the environment for learning than whether they know what a focus is.
Yeah. Cool, just,
Right.
and then I had another question.
Yes.
So when you were talking about sort of like the spectrum of, was it spectrum of?
Tinkerability, yeah.
So.
I feel like the extreme would be like free parts play, where you're just like, you just give kids a bunch of things and like, they just do whatever they want.
100%, yeah.
Were any of the things that you looked at like pretty much just free parts play?
Oh, actually, I mean, I guess Lego counts as one of those, right? Where you have a bunch, hundreds of different things and then you can create whatever you want. A lot in case of the tech-based or computational devices, I did not see that really.
Cool.
But one thing that you always have to be wary of is, let me see if I have this quote in the notes. Because a lot of times constructionism and tinkering is mistaken as like just casual messing around with no goal. And that's fair. That's a question I get from Ellen a lot of times when I'm trying to justify. Yeah, exactly. But Albert, when he talked about this, very much focused on how the environment and the tools should offer opportunities for conscious engagement and reflection, which is what's promoting the learning. So it shouldn't just be casual messing around, but there should be an opportunity and a context to think about, wait, why is that happening? So in your case, in here, if you try it out a few different ways, you might start wondering, why did it start going fast over there? Or why did the shape get so weirdly elongated if I move this far apart?
Yeah.
Yeah.
Cool. There's a nonprofit in like Somerville, Massachusetts, where it's free parts play, but like they theme different boxes around different concepts. So like reflection is like all like very shiny stuff, or like mirrors, mirror pieces. Then like colors or like physics, like they'll have like spheres that can roll down slowly.
That's very cool. Okay.
So that's what I was thinking of for like free parts play.
Yeah. Yeah, thank you. Any other questions? I was afraid of running over, so.
How, like. The begging question in my mind is, this, and I went around and I looked at a lot of people, this seems very programmed. In terms of, okay, what is it going to do? Like the insight, we're all getting the same insight because it's pre-programmed versus, oh, wait a minute. And I did this on purpose. I actually created a mixed up word on mine that had to do with the ellipse and the orbit syzygy, right? And it didn't pick that up.
Yes.
But I would hope to have that as an insight versus, okay, everybody's doing an orbit. So how do you take pre-program bias out of the tinkering such that an insight can come out that's unique and special for my engagement? You know what I'm saying?
That's a good question. Yeah, 100%. So I'll start by talking about how this emerged from Cartoonimator, in which case Cartoonimator was completely free form. So and I can demonstrate that as well. It doesn't work on my phone anyway. But so there the idea was you don't just have these three things, you could have 5 different objects and you are defining the exact movement. But in this case, we try to bring in that pre-coded thing because we want to embed physics in it and have them use this as a platform for experimentation. So you can't really just because you were able to create the syzygy, which wouldn't be possible in real space, of course. But that's what an interface like that's still open-ended lets you do. And I think there's that aspect of working on that spectrum about how expressive or how open-ended you want the interaction to be. we could have defined it in a way that doing that isn't even possible, and it breaks, it stops, it tells you to define, move the foci at exactly this point and then capture again. But in so many,
Lucy raised her hand.
oh, okay,
Yeah.
so many times we've actually seen people make an asteroid animation where they put the planet between the two focals, which obviously is probably Big Bang level end of the world, but it works.
Yeah.
And then you see a weird line instead of an ellipse.
At least a black hole.
Yeah. But I think there's something about getting to those insights yourself. But again, I don't see any of this as an independent learning tool. It always has to be contextualized in a setting with an educator where they can guide you through those questions. Like, why is that a straight line? Because that shouldn't be a thing. Did that answer your question?
Yeah, Lucy has her hand up.
We can do that.
Yeah.
Yes, go for it.
Yeah, related to that, I guess my question for your workshop and like when you've done this is how much like concept of the learning principle you're giving to people beforehand. Like, like in this case, I feel like it was sort of like let's see what happens. Like you guys don't really know what's going on right now, and that's fun. But like in the, in the application with did you do it with high schoolers? Is that what you said?
No, this must be undergraduate students.
Yeah, undergrad. Yeah.
yeah.
So I was just wondering, like in that case, they like have had some basic introduction to the law and like, obviously it's in the context of the science learning environment and whatnot. Like all of that might help them to like map those learning principles onto the, creative process, and that
Yes.
is important. Right. So I just was
Oh, yeah. Thank you for that question. And yeah, that gives me an opportunity to talk about how we've been using this. So we've been collaborating with the instructors at CU Denver who teach the intro astronomy course. And what's really interesting about that course is that it's generally meant for non-majors. So they're not students of astronomy who want to go deeper into how how the physics exactly works in something like this, but they're usually students from business or arts or a lot of different majors. And what they really saw potential in here was that it's a way for them to draw them into the concept of Kepler's laws through something that they're already interested in, which is maybe drawing or animation. Now, the way we used it in their classroom was they had gotten an introduction to what a Kepler's law or what each of the Kepler's laws are. And in a very similar way to I did back in high school, where you're just given these three laws. The first is that it should be an ellipse. The second is that it moves faster near the sun. And the third is the size is proportional to the time it takes to go around the orbit. And I don't know why I still remember these three, but that's how my schooling was, where we didn't really experiment with this. Here, the idea was that they learn about what these three laws are, and then they go free form, explore the actual behavior in the form of this simulation, in terms of how they can move the things around to get different types of orbit and then compare and contrast between the two. What we did very recently in July, in their summer class. So we've been doing this for like the whole year. So we did it in fall, then spring, and then summer. And summer was a new type of activity where they first interacted with this in a more playful format, where they were creating any type of orbit that they wanted. And then they actually did lab experiments on these simulations to prove each of the three laws. So they're not just learning that this is the law that's dictating the simulation, but they went in and actually measured the speed of the asteroid near the sun versus away from the sun and compared the two and things like that. So like that ties into the lab-based in investigative, what's the word? Inquiry-based learning that happens a lot in physics and STEM in general. So that's, and like we're gonna be going again in fall to do it in a similar fashion, where they first explore the ideas and explore the space of interaction with freeform, different types of simulations that they can make. And then they try to tie those concretely to each of the three laws to learn about, or to kind of validate for themselves that those laws actually hold on. Does that answer your question?
Yeah, great context. And I figured you were, yeah. I just wasn't sure like to what extent like you were, I guess they were getting content before the actual workshop took place, but yeah. No, it's
Yeah,
super cool.
this was a very different setting, and I just wanted to see how it happens, because we haven't done it with a room full of people where most of them didn't know Kepler's laws, which is great. That
Well-
means you had a healthy high school environment.
Well, it seems like in a way what you're doing is you're developing language in real time in order to create a better abstraction space for the brain, the
Mhm.
mind to take it in.
Yeah,
But then there's that criteria, okay, for this particular mind, where is that threshold where I need to develop a different language, which takes time,
Mhm.
right? In order to get the insights I need versus I don't need a different language. I can go with the base language to get the abstraction in my mind to
Right.
hold the concept of the insight. Do you know, because that limit, that seemed to be an important thing in terms of the return on investment of why would you deploy this in any kind of a project?
right.
Yeah.
I think so. By language, do you mean like specific ways to talk about these concepts, or do you mean?
That's one way of putting it,
Right.
but it really is the development of the like it's a language theory problem that at the heart of what you're doing,
Yeah,
right?
that's the first way I've had somebody describe it to me in that way, and I like that. Yeah, because it's kind of a way to reason with these concepts that are really abstract. And specifically in this context of astronomy and Kepler's laws, because this is something that you won't experience in day-to-day life. You won't like in case of gravity, you would see a ball falling and you'll see that it falls and it gets faster as it goes down. But with space, that's not something you can observe and develop language for. So I think one motivation specifically in case of astronomy was to highlight or uncover these invisible phenomena, invisible to daily life, for example, in a way that it's still real and lets you develop the reasoning behind it.
And enriches your mind map in such a way, like love, right?
Yeah.
In English, love is that.
Mhm.
And what is it, France or Italy, there's like 7 different ways of describing love.
Yeah.
So do you need to learn Italian in order to really understand what love is as an abstraction? It's like that as an
Yeah.
analogy to what you're doing.
I see.
At what level do you, how do I need to understand an ellipse? And do I need to have this, do I need to pay the time and effort
Mhm.
to get that insight within my construct of mind?
Yeah.
You know, because ROI is important when you say, oh, how could this be, Medtronic robot interaction in the operating room? How could this be deployed and is it worth it? I think that's an important question to be asking in your PhD thesis.
Yeah. That does give me something. I like that. You should talk more.
Or maybe I'm just hallucinating.
No. It's like it's talking about reasoning with tangible interfaces on a different level than like just day to day. You learn this concept or you develop an understanding.
How does your mind actually use its own formed abstraction space to hold a concept?
Yeah.
And do you need to develop a different language to be able to get the insight in it you need for whatever you're trying to do in the future? And there's a ecosystem there.
There's a
that you
whole recall.
have to look at the cost.
thing about it, right?
So I think language theory is probably really important for you to
Okay.
at least look at in terms of the cost analysis, if that makes sense.
Okay.
I think you could look at structure mapping theory as like a.
Yep.
Structure mapping theory.
Yep.
Zoom is getting so smart, it just asked me to confirm our speaking language and it thinks we're talking in Persian. I'm just kidding.
Confirm your speaking language.
Case in point.
Wow.
Literally.
Whoa. And hallucinating, yes.
And your other option, if you want to skip some of the higher level theory and jump into like the learning sciences, part of that is to just kind of frame this in terms of instructional scaffolding and like what has to come before it and what has to come after it. That's a very like tangible way to think about where this sits in like a curriculum.
Yeah.
That's more grounded. That's well put.
In terms of the curriculum, right? Thank you.
I thought it could be, you could think of too, like what other related systems in the class like this can help, you know, the learners to generalize to, you know, like how can you design the interaction to help them to learn not only this one law, but also transfer to other, you know, related principles. And I think all of that is very related to what everybody's been talking about.
Yes.
So, yeah.
I think the generalizable aspect is very important, and that's something we've been discussing for sure. This was like originally the Kepler's laws, they do it in that classroom, is using two thumbtacks and a piece of string, where they draw the ellipse and then they take measurements to figure out the eccentricity, and that's it. So I think like this ties into what I mentioned earlier, is like there's the generally broader idea of experimenting with these concepts that you wouldn't be able to in a real context, but using a tangible representation to kind of imitate that experimental inquiry based learning. Like you can in physics labs, you can use lenses and electric circuits to look at the Ohm's law or the what's the lens law? Who's the guy who did the lens law? My bad. But then there's things like nuclear physics where you can't actually in a high school or undergrad level classroom actually experiment with, oh, what happens if I put two neutrons together? Yeah, so I think we have a lot of work to do in terms of generalizing it, finding all these other types of concepts where this can be used, which should be better for the ROI.
Yeah. Very interesting.
More questions? Yes, we're basically at time as well.
Yeah.
Thank you, everybody.
Thank you.